All right, let's jump right in. Welcome to This Explainer. Today, we're unpacking one of the absolute most awe-inspiring feats of modern engineering out there, the block erection sequence of massive ships. Now, if you've ever seen a time-lapse animation of a dry dock where a colossal steel behemoth just comes together from a bunch of giant parts into a fully assembled vessel in like 30 seconds, it is wild. It's a total masterclass in scale and precision, and today we're going to see exactly how they pull it off.
But first, you gotta wonder what happens if you build a massive ship in the wrong order. Seriously, imagine a shipyard simply grabbing these giant prefabricated steel boxes, these blocks, and just stacking them randomly as they arrive on site. What do you think would actually happen? Well, spoiler alert, you absolutely cannot just place blocks in any order. The erection sequence is a rigidly pre-planned construction plan. Skipping that sequence doesn't just make things inefficient, it leads to massive, literally ship-breaking structural distortion. We're talking dangerous instability. You'd end up with connections that become physically impossible to reach and weld. That translates to multi-million-dollar rework, and you might end up with a ship that never actually floats right. So yeah, the stakes are incredibly high. Section 1. The Giant 3D Puzzle. So, building a ship is essentially a highly calculated 3D puzzle. I know people always compare it to giant Lego bricks, but honestly, actually scratch that. It's way more complex than Lego. Because physics, sequence, and absolute precision are critical at every single step. Every individual piece has a designated spot, and it has to arrive at that exact spot at precisely the right time. Section 2. Starting in the engine room. Okay, let's dive into this. Where do you even begin? Well, erection almost always starts at the aft of the ship, the rear engine room region. But why start at the back? There's actually a really satisfying logic to it. This area contains the heaviest structural blocks on the entire vessel. It also involves the most complex outfitting and intricate piping. And this is the real kicker. It requires the absolute longest lead time to install all that heavy equipment. This specific zone is called the aft machinery space. It's the heart of the ship, housing the main engine, the propulsion machinery, the generators, the shaft line, the whole shebang. By establishing this block first, shipbuilders buy themselves the longest possible window to carefully install and connect all that vital equipment before the rest of the hull is closed up around it. Moving to Section 3. The build-up sequence. So from that very first block in the aft machinery space, the ship literally grows in two directions simultaneously. It moves forward along the ship's length, and at the exact same time, it builds upward in height. First, the aft bottom blocks are laid down to establish the structural baseline, the keel. Then, more bottom blocks are placed, moving forward to expand that baseline. Finally, the upper blocks are stacked on top to build out the height. The absolute crucial takeaway here is that you've got to get the foundation right. Those bottom blocks establish the keel baseline, so upper blocks can only follow once the lower ones are completely welded and perfectly aligned. And by completing the forward part of the hull last, the teams working in that complex aft machinery space get maximum time to finish their jobs. It's a beautifully orchestrated dance. Section 4. The critical joint. Now, what's really interesting about this next point is this tiny, almost unbelievably small number, 3 millimeters. That is the maximum allowable misalignment when bringing two of these giant ship blocks together. Just think about that extreme juxtaposition for a second. We are dealing with hundreds of tons of prefabricated steel, massive chunks of metal being hoisted through the air by cranes. Yet, when those structural members finally meet across a joint, the tolerance for error is a measly 3 millimeters. The sheer massive weight of the steel contrasted with those incredibly tiny margins of error, honestly, it's enough to make any engineer sweat. So how do they hit that mark? It takes an intense precision alignment process. First, the blocks are set on precisely surveyed keel blocks. Then, surveyors bring out advanced optical instruments called total stations to double and triple check the alignment. If it's even slightly off, they use hydraulic jacks to literally nudge these mountains of steel into position. And no joke, until that strict 3 millimeter tolerance is perfectly met, absolutely no permanent structural welding begins. Let's look at Section 5, Scaling Up. Mega blocks. Now, modern large yards take this efficiency a step further. They use what are called mega blocks, and it's exactly what it sounds like. Instead of lifting a bunch of standard blocks into the dry dock one by one, they pre-assemble multiple standard blocks into one giant unified block in a highly controlled workshop area. A mega block can span the entire width of the ship, port to starboard, and stretch from the keel all the way up to the upper deck. And these numbers right here, this proves why mega blocks are a total game changer for large ships. Let's put this into perspective. Using standard blocks, a ship might require 150 separate crane lifts and 149 really difficult, complex joints welded right there in the dock. But with mega blocks, that drops to just 10 to 15 crane lifts and maybe 11 berth joints. That is a massive, massive reduction in time-consuming work out on the berth. But, there's always a catch. This level of efficiency requires a huge upfront investment. To lift a single megablock, a shipyard needs absolute monster gantry cranes, capable of lifting up to 3,000 tons. That is a gigantic capital expense, but the economics make sense because it drastically reduces the time a ship ties up the really valuable real estate of the building dock. I love how our source material frames this. It says the megablock strategy does not change what is built. It changes how efficiently it is assembled. It essentially takes all that painstaking, precise welding work out of the elements in the dry dock and moves it into an easier, controlled workshop environment.
And that brings us to our conclusion, a high-stakes calculation. So, let's recap what we've learned today. The block erection sequence is a marvel. It always kicks off in the aft machinery space, building both forward and upward. As those massive blocks meet, hitting that 3mm alignment tolerance is an absolute must before any welding starts. Because of this, the entire sequence is rigidly pre-planned. Any deviation means stopping everything for a full reevaluation. And to speed it all up, mega blocks are used to radically reduce time spent in the dock. So I'll leave you with this final, crazy thought to chew on. As ships get bigger and yards use fewer but heavier mega blocks to boost efficiency, what is the physical limit to how large a single block can actually become? Are we going to see 5,000-ton or maybe 10,000-ton blocks in the future? It's a fascinating question about the sheer scale of tomorrow's mega engineering. Keep exploring, keep questioning, and thank you so much for joining me on this explainer.